Welcome back. In the second part of this lecture, we're going to talk about a better algorithm for univariate Gaussian mean estimation. So in particular, we're going to prove this following theorem. So we're going to show that there exists an epsilon dp algorithm, which estimates the mean of n, say mu 1, where we're given the constraint that mu is less than or equal to r, recall, that's the bound on the mean, and to accuracy alpha. And the number of samples we require is n equals O tilde, again ignoring log factors because they're not too important here, 1 over alpha squared plus 1 over alpha epsilon plus log r over epsilon. So yeah, we're going to talk to, so let me say that the first two terms here are the exact same as we have in the simple problem of privately estimating the parameter for Bernoulli distribution. So that's just 1 over alpha squared plus 1 over alpha epsilon. Yeah, these are nice and simple. The sort of added complexity of the case, since we have an unbounded data set, and all we're relying on the fact that this is a Gaussian distribution. This third term here is the additional cost due to the unbounded range. So you'll note that before, let's compare this with the previous thing, which was plus r over alpha epsilon in terms of instead of the second two terms. So this is improved significantly because we reduced the dependence on r from linear to logarithmic. So this is an exponential improvement in the dependence on this parameter r. That can save us a lot and lets us, especially even in practice, do significantly better in terms of the dependence on this parameter. So yeah, that's the real benefit. And also I'll comment that this is essentially the optimal sample complexity for this problem. The first term is optimal even in the non-private setting. We can't go beyond this sample complexity. And the second and third terms can be proved via packing lower bounds as usual. So let's see a proof of this. In fact, we're going to show you two different proofs. There's actually even a third one, which is based on the exponential mechanism in place of the histogram-based approach in the first approach I'm going to tell you today. But we'll skip the exponential mechanism, and I encourage you to try working it out yourself just to see how that works. So this histogram-based approach is the first one that we'll see. And this was first used by Karwa and Badan. I'll write the names out. That's not actually how you spell Badan, Karwa and Badan in 2018. So the procedure is divided into two parts. The first part is obtain a coarse estimate of the mean. So this will give us an estimate up to, say, plus or minus, say, like a constant, not exactly a constant, but essentially getting a coarse estimate which only gets within a constant of the right answer. And this will take O tilde of like log r over epsilon. And then the second step is to do a fine estimate, which will take something more like O tilde of 1 over alpha squared plus 1 over alpha epsilon. So yeah, you can see that this there's two different steps, and they both incur different costs in terms of how many samples they need. So let's break this down into to the two parts and see how they work. So the first step will be a histogram-based approach, as like the title here suggests. Yeah, the idea is that we're going to split the interval. Remember what we can do is we can say that all the data is going to be within this interval with sort of high probability. Yeah, minus r minus O square root n plus O of square root log n. Yeah, all the data will be in this interval with high probability. So what we do is divide this into intervals of the appropriate width. In particular, we divide it into, say, O of r divided by square root log n intervals of width O of square root log n. So yeah, I would basically just chop it up in the obvious way. You know, the first interval is going to be the first log n, and the second log n, third log n, and so on. And this will give us overall O of r over square root log n intervals, and we can upper bound this by, say, O of r. Okay, so that's the overall bound on the number of intervals and each of their width. So the idea is the following. These are all pretty wide, you know, they're O of square root log n, and we said that all the samples from the Gaussian will fall into an interval of square root log n. So let me try to sketch you out a picture of what this kind of looks like. So, you know, here's the interval roughly from like minus r to r, maybe like, you know, plus this O of square root log n if you really care, but I'll just leave that out just for simplicity. So this is what the entire interval looks like, and the idea is that we have, there's some Gaussian data set. So like, what does the Gaussian look like? Looks something like this. And, you know, we have a data set which is generated from this and looks something like this. And like I said, the width of this interval containing all the data set points will be of width O of square root log n. So what we're going to do is we're going to chop this up into intervals of width, say O of square root log n, like this, 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 I guess this, and so on. And what is the intuition? Well, you know, most of these intervals are going to be entirely empty, but a few of them will have a significant number of points. For example, like this one will have some points. So let's kind of draw this as a type of histogram. This will be 0, this will be 0, this will be non-zero. It'll be sort of some small value here. And when I say a histogram, this just means how many points fall into this interval. This one will be fairly sizable because this is where the majority of points fall. And this one will be tiny, maybe like no points fall here. But yeah, let's just put a few. And then all of the rest of these will be pretty much exactly 0. So this is the idea. We have this interval overall minus r to r where we know the points lie. And the idea is we know that there should be a couple of these bins which have a significant number of points, which is essentially the ones corresponding to where the Gaussian lies. And we chose the width very specifically in order to guarantee that maybe only like 1 or 2 or 3 of these intervals have any significant number of points. So what we're essentially going to do is we're going to try to find this, you know, this point here essentially, which bucket, which sub-interval within the overall interval has a significant point of number of points. Because if we can find the interval which contains most of the points, then this also contains the mean. The whole idea is we're going to try to just get a coarse estimate of the mean and try to find the bucket in which the mean lies, or if otherwise, you know, the one next to it. Okay, so what we can do is, again, recall that we can use Laplace histograms. Or, yeah, Laplace histograms, or say, you know, pure DP histograms, whatever you want to call them. But the idea is all you have to do is add Laplace 1 over epsilon noise to each count. On each count. And what will that do? That'll give us some noisy counts, which look kind of like the following, let's say. You know, the resulting noisy count here will be something like, I don't know, maybe it'll be up here. Maybe this one will be down here. Maybe this one will be up here, let's say. Maybe this one will be down. Let's put this a little bit higher just for illustrative purposes. Maybe this one will be down here. This one will be maybe up here, and so on. Like these will be whatever values they are. Okay, so ... Now the idea is that what does the Laplace histogram say? It says that the max error incurred, basically the maximum difference between the true count and the privatized count, this is going to be less than or equal to log of the number of bins divided by epsilon. Now here, since the number of bins we have is essentially, like I said, we can upper bound the number of bins we have, the number of intervals here we have by r. So this is going to be, the max error in any interval will be at most log r over epsilon. Okay, so that tells us how wrong any answer could be. Now let's take a look at how many points fall in the heaviest bin. Well, based on the way we sort of chose the width of this interval, well, it's not too hard to see that essentially the kind of, what is the minimum number of points that can fall into the heaviest bin without privacy? Well, the minimum would just be sort of n over 2 if essentially the point falls right at the boundary. You know, if you had something where it's like split evenly between this and this, then that would cause the max bin to be n over 2. So essentially what we want is that the value of n, the max count in the histogram is going to be greater than any of these any of these other ones which are empty. That means that we're definitely not going to output any of these empty bins. We're either going to output the one with the highest count or one of its neighbors which have a non-zero count. So if we want to guarantee that, we need that, say, n over 2 minus log r over epsilon. We want this to be greater than 0 plus log r over epsilon. And this is just a sort of rough thing, I'm leaving out constants, but the idea is that, this is the lowest the count in the maximum bin could be, if we know that the max error is the most log r over epsilon, and this is the highest the count in the min bin could be, and an empty bin could be, if, again, we bound the error by the same thing. So this implies that we need, say, n to be greater than or equal to log r over epsilon. If this happens, then, what that guarantees is no matter how the noise shows up for sort of these empty bins, it won't supersede the noise in the bin with the most. Of course, you might instead get one of the other non-empty bins, but that's fine. So for example, in this case with the green noise things, you can see that this is higher than all the empty bins. If you excuse my poor drawing skills, I'll say that this is like here. So that's lower than that. But you can see that in fact the one that we do return as being sort of the highest is going to be this one right here. So, okay, the idea is that, just to sort of summarize the step, if we have log of r over epsilon points, at least in the data set, then that will give us something which gives us a very coarse estimate of the mean. In the sense, what we can do is we can take the interval corresponding to whichever one we picked out, plus its sort of two neighbors. So we're going to, pick this as well as the one on the left and the one on the right, and we'll say, okay, so this interval here is going to contain the true mean. And indeed, we're right, it's right here. So let's summarize this with a lemma. So our lemma will be the following. So there's an epsilon dp algo. It finds an interval I such that mu is in I. And we have that, and of course the same sort of things as before, and mu1, mu is less than or equal to r in terms of magnitude. Those are the same things we had before, but what we need now is that n is greater than or equal to O tilde of, say, log r over epsilon. This will imply that the width of I will be at most O of square root log n. Because remember, you just pick the one which has sort of the highest privatized count, and take the one to its left and the one to its right. This will be a private estimate, and it'll also have bounded width like this. So at this point, we're almost done with this algorithm. This is like the sort of lemma, which is the course estimate step. Yeah, this is the course estimates lemma, and what this tells us is that we get down to essentially not a constant width quite, but you know, close to constant width. So recall that way back up here. Let's recall the naive approach we had. We said that you know, if we could do this kind of naive approach, which would work if we had, and this would give us sort of a great sample complexity, if we knew that R was going to be a constant, or yeah, if it would be constant, then this would be like near optimal, because we can't get better than 1 over alpha squared plus 1 over alpha epsilon. The thing is, we haven't got down to R equals 1, but we're actually fairly close. So let's just write this out here. You know, so now we have that, you know, we have some interval where which contains a mean. So this is going to be our interval I, you know, that we have width of I is less than or equal to O of square root log n. And remember that if we let R be equal to the width of the, or at least 1/2 the width of the interval, which contains our true mean, then we have the following theorem. So we know that essentially we have that R is less than or equal to O of square root log n. We're down to a very narrow uncertainty about where our mean is. So at this point, all we need to do is run the algorithm claimed by, you know, the naive approach here, and that'll get us the right sample complexity. It tells us that we need that n is equal to O of 1 over alpha squared plus essentially square root log n over alpha epsilon. And like I said, this is sort of, if you kind of do the math and adjust this is just going to result in sort of logarithmic factors here. So this is just going to be equal to, again, O tilde of 1 over alpha squared plus 1 over alpha epsilon. Right, this is what did we just do? Essentially, this follows a two-step procedure where the first step, we, you know, in the whole thing, we find this do this histogram approach and find the narrower interval where the data roughly lies. And then what we do is we essentially run the naive algorithm, just assuming all the data lies within, or assuming that the true mean lies in this much narrower interval than before. So this is the approach that we did in the naive approach. And yeah, it gets a good accuracy here. Okay. So one final note I'll make here is that, okay, this gives you the right sample complexity that we wanted. If you just add the cost of the second step to the cost of the first step, which is right here. I'll comment that there's sort of two steps here, so you have to allocate epsilon over 2 privacy budget for each, just so that by basic composition it'll add up to epsilon overall. Yeah, so that gives us overall this theorem which I claimed here. So this is a great approach. It's very nice. The downside is the fact that it's not going to scale very well to the multivariate setting. So I'm going to introduce now another approach, which is sort of similar ideas, but also a little bit different, and I guess even simpler ideas in my mind, which will also get the same sample complexity essentially. Except it'll be an approach which is easier to describe how to apply it to the multivariate setting and more complicated situations as well. And this will be the shrinking confidence interval approach. This is in a very recent paper that's at NeurIPS this year by Biswas, Dong, myself, and John Ullman. Like I said, it's very simple. All you need, it doesn't need anything except the Laplace mechanism. That's all it is. Just an iterative application of the Laplace mechanism. And rather than having a coarse estimation step, then a fine estimation step, like in the previous slide, or in the previous slide, I guess. previous page. This time we're going to iteratively make gradual refinements. We're going to start with a very, like, the general interval that has mu is less than or equal to r. Then we're going to shrink it a little bit, and then shrink it more, and then shrink it more, and shrink it more, until eventually we get a fairly narrow interval containing the true mean, and then we can just do sort of the fine estimation step as we had described before. So let's take a step even further back. Let's return to the naive approach and just extend it slightly. So let's recall what the naive method is. It's two steps. It clips data. It clips the data to some interval. Noises the empirical mean after that. So we're going to extend this approach with just the addition of a final. We're going to extend this approach with just a final step. This is that plus a new confidence interval on where the mean lies. So the idea is, we're kind of always going to keep some estimate of where the mean lies. We start with a, guaranteed interval of where the mean lies, but we're going to keep shrinking our interval on where the mean lies until we get something which is sufficiently narrow. So let's describe, a simple algorithm, and then this will give you the main idea behind the overall approach. So the first thing we're going to do is clip the data set to this interval minus r minus O of square root log n and r plus O of square root log n. And if any data point lands outside this range, move it to the nearest endpoint of the range. So the second part is you just compute the privatized estimate. This is just going to, I'll let z be a variable which represents it. And again, I'll use this f to be the clipping function. And you just add Laplace noise to r plus O of square root log n over epsilon n. And so this is the exact same algorithm as we had before. The difference now is that instead of returning, before we would just do this, we would just return z, but now we're going to return an interval centered at z of width, the following width, O of 1 over square root n plus r plus square root log n over epsilon n. So yeah, this is a bit curious. We now have added a step to the naive method. So before, what we did was we did just steps 1 and 2, and we hoped that step 2 would give us a very accurate approach. The thing is, if we wanted step 2 to give us an accurate approach right from the get-go, we would need a very significant amount of data. However, we're going to need something only weaker than that. We're going to just want to return something that's just a little bit better than our starting width, and we'll sort of build on that repeatedly. So here's the algorithm, and here's the claims I'm going to make about it. There's two claims which I'm going to sort of bundle together. First of all is sort of one, if n is greater than or equal to of 1 over epsilon, and r is, say, greater than or equal to c times square root log n, for some absolute constant c, then the interval returned is going to be a constant factor smaller than the initial interval. Let's write that. So yeah, essentially we make a constant factor of progress in terms of our shrinking our interval in each time step. The second thing is if the data set x, x1 through xn is truly Gaussian, so if it's actually from n0, 1, then the interval that you return will contain x, or contain mu with high probability. So these are two different guarantees. The first one just says that sort of deterministically, no matter what, then the returned interval will be a constant factor smaller. The second one says that the interval will contain the mean, assuming that the data set was actually from a Gaussian with high probability. So these are two different things, and we'll sort of prove them both. So let's prove them both. The first one is fairly simple to see, just by looking at essentially the first and the last line. So what is our starting interval? Like, okay, I said the return interval is a constant factor smaller than what? Well, the starting interval, like I said, is going to be minus r to r. You might think it's like minus r minus log n, or square root log n, or r plus to r plus square root log n. Well, that's sort of how we widen it. But initially, we just have some mu that mu is in this. And the claim is that we get a constant factor smaller. So the final interval is of width something like, the final interval is of width O of 1 over square root n plus r plus square root log n over epsilon n. And so now all we have to do is take n to be a sufficiently, if we take n to be greater than or equal to O of 1 over epsilon, say let me in fact throw in a constant here just to be sort of like silly, just so that you get the idea. Say you set n to be greater than 100 over epsilon, then in that case, what will you have here? Then the final width is going to be, say, less than or equal to, O of, let's just write some numbers here. Like technically there's some hidden constant, but like it should look something like the following. Here you have is less than or equal to, say, square root epsilon over 10 or something. And here you're going to have something, if you just plug in n for this, then you're going to have that this is less than or equal to plus r over 100 plus, square root log n over 100 as well. So the idea is we started with something which had an initial width of this width is 2r. And now we have something which this is tiny. This is, if we have this condition on r being sufficiently large to start with, then this is going to be negligible as well. So really we went to from something like 2r to r over 100. So this is indeed a constant factor improvement. And we didn't even need that many samples to make a constant factor improvement. Before, we needed, say, r over alpha epsilon in order to get down to, say, alpha accuracy. But here we just wanted to reduce the width by a constant factor. So all we need is, say, 1 over epsilon in terms of the amount of data. Okay, so that's sort of the easier part. Well, I guess then neither of them is very hard. The other claim is the fact that this returned interval, which is centered at z of width, whatever, this is, the claim is that this contains the true mean mu. And let's see how we show that. Well, the idea is, first of all, suppose z is going to be our estimate in the second step, where we compute the private estimate and then we add noise. If z had no error due to sampling, process, and the noise, then z would be equal to mu if there was no noise, if there was no error. Kind of almost by definition, yeah. But instead, let's say we try to account for this error. What is the difference between the value of z, the statistic, and the true mean? Well, writing it out as we have before, bounding it by the absolute value of the true, let's just write this 1 over n summation of, say, xi minus mu plus the sort of magnitude of the noise. So if you can bound the difference between this the statistic you get in step 2 with the true mean, and this difference is bounded between by the sampling error as well as the error due to noise. And you can bound these by the same things we've bounded them before: O of 1 over square root n just due to sampling, and O of r plus square root log n over n epsilon, just as before. Therefore, what we can say from this is, imagine we drew an interval of this width around z, then this inequality here essentially shows that that interval will contain mu, with high probability, of course, which is sort of implicit in both of these arguments. But yeah, just says that essentially we can draw an interval of this width around mu, and that will contain, draw an interval of this width around z, and that will contain mu with high probability. And that concludes the proof of this little claims here, that this additional step where we return an interval centered at z of an appropriate width will make a constant factor improvement and contain the true mean. So let me try to sketch out what this type of thing did. I gave you a drawing before. Right, let me give you another drawing. So it's kind of the following setup. So we have here that this is minus r to r. And there's some Gaussian somewhere, so like that gives us something like, here's the Gaussian, let's say, and this corresponds to a lot of data over here, and then spaced more out here. And what is the algorithm? The algorithm first says, clip the data to this interval. Let me do this in a different color. So clip the data to this interval, and add noise, and compute the empirical mean. That might give you something that lands right about, I don't know, here, let's say. This is sort of, what is it? Something like 1 over n summation of xi plus Laplace of magnitude, say 2r over n epsilon. Roughly, something like that. That's this point right here, z. Now, the idea is, of course, this is a terrible estimate of the mean, but it tells you also that this is not totally far away from the true mean. In particular, what you can do is say that, okay, so this lands right here. Well, if we draw an interval around this somewhere, like centered around this, say go over here and go over here, then this interval now will contain the true mean, which is true. You can see that the true mean mu is indeed in this interval. And the second thing, as you can see, is sort of a constant factor improvement from what we had before. And yeah, that's definitely true as well. This is sort of roughly half the size, let's say, of the previous interval. So that's the idea. We started with a very wide interval. We reduced it by a constant factor. If you did it again, maybe you'd get an estimate which is somewhere around here, and that would give you some smaller interval like this, and then maybe you would get an interval like, I don't know, like this, something like this, and then so on until eventually you get something very small. And yeah, that's the idea behind what the, sorry, I'm getting ahead of myself. Essentially, all I described here was this one-step procedure where you would just go from this overall wide minus r to r interval to this blue interval here. But essentially, what this is doing, or what we would like to do really, is not just run it once to get a smaller interval, but run it again and again like we're doing here. In particular, we can say that since running the iteration once causes a constant factor improvement in the width, then running the algorithm t equals O of log r iterations the idea is if each time you run it, it reduces it, say, from r to r over 2 to r over 4 and so on. That implies if you run it t equals log r iterations in total, then you'll be left with an interval of width. You know, it'll give you an interval of width equals O of square root log n, I guess. Like, I don't know, I'm sweeping some details under the rug here, but like, yeah, ideally it would reduce the width to O of 1, but recall that we had this like special condition here that we can't really do much better once we get down to r equals c times square root log n. So this will get us down to width of square root log n. So the one catch here, this essentially says we can start with something which is r and get it all the way down to O of square root log n. The catch here is the fact that we did t iterations. So if we just do basic composition, that would make it t e epsilon differentially private. What we're going to do instead is we're going to set you know, epsilon prime is equal to epsilon over t. So like essentially we're just going to rescale the privacy parameter here in order to be epsilon over t instead, basically, you know, rescaling this to be epsilon over log r. And if you do this sort of adjustment everywhere, changing epsilon to be epsilon over log r, then the effect will be here, I guess, sorry, I wrote over this, but we're going to now need that n is greater than or equal to log r over epsilon, and that'll give you the condition that we need. I'm not going to bother changing all these other things, but yeah, let me just change it one more time here. We need essentially n is going to be greater than or equal to log r over epsilon, just because of the fact that we're using composition over log r rounds. And this, hopefully this log r over epsilon should look familiar to you by now, because you know, we need now, let me just write this, n is greater than or equal to log r over epsilon. Oh, if this. Again, this hopefully looks familiar just because of the fact that this is exactly what we had, sorry, in the theorem statement, log r over epsilon samples. All right, so with that out of the way, now we've reduced the overall width from like r to square root log n. Now for this one, all we need is that, yeah, all we need now to finish it off is use the sort of naive algorithm. So recall we're kind of in the case where now r equals O of square root log n. And once again, we can finish this just as we did in the previous one, where, you know, I won't bother writing it again. You know, maybe I'll just copy paste it. Where we complete it just by running the naive algorithm. Oh, whoa. Yeah, we completed just by running the naive algorithm, which costs us 1 over alpha squared plus square root log n over alpha epsilon. And again, sort of rearranging and removing the log factors, this gives us something which is this optimal sample complexity that we wanted. So yeah, let me just highlight the key things here. Like basically the final sample complexity, let's just write them in orange boxes, or let's say red boxes here. The final sample complexity will be this for the final step, but all of the sort of shrinking of this confidence intervals, that will take this many samples. It's poorly written, but it's log r over epsilon. So just summing those two gives us the exact same theorem as you saw before. Okay, so this is, I think, you know, there's two different approaches of getting the this estimator for the mean, which achieves a accuracy, or it achieves accuracy epsilon given this many samples, and importantly reduce the dependence on this parameter r from linear to logarithmic. Yeah, so this was just for a very basic setting. In the final part of this lecture, we're going to go beyond this simple setting and show how this type of shrinking confidence interval approach can be quite a bit more general. We're going to sort of mention one more setting, multivariate mean estimation, but it goes even beyond that. So please stay tuned and join us for the third part.